This is a new chapter called as data representation. By now, most of you must be aware that computers do not deal with decimal number system. For computers, the processing is always in terms of discrete values, that is zeros and ones. So ones and zeros are known as binary digits. You have the binary number system where the only digits permitted are zeros and ones, and they are also known as bits, which is an abbreviation of B and ITS. So in order to develop a good understanding of the working of a computer system, it is essential to have a decent knowledge of the binary number system, octal number system, the hexadecimal number system, and how to convert numbers between each of the number system to the other. Before we head into talking about binary, octal, decimal, or hexadecimal, let's understand a fundamental concept of what is a non-positional number system. So, if you look at it, an example of a non-positional number system would be your Roman numbers. In Roman numbers, 1 is represented as like this, 5 is represented like this, 10 is X, 50 is L, 100 is C, 500 is D, and 1000 is M. Now, the difference between the Roman number system and the decimal number system we use is, irrespective of the occurrence of the position of this, the value remains the same. So symbols simply represent the value. They do not represent the value based on the position. What I mean here is, take a look at this. Suppose I have a number 236. So 6 is in the units, tens and hundreds. So it is 6 into 1, 30 into 10, 2 into 2 into 100, so it is 200, so it becomes 236. 623 is 6 into 100, 2 into 10, which is 20, and 3 into 1, which happens to be 3. So this number is 623. So although the digits are the same, but based on their position, they get different values. So this is an example of a this is an example of a positional number system. In a non-positional number system like the Roman numbers, different symbols are used to represent numbers. So here I have said all the numbers are represented here. So here if you see, this is 1, this is 1. But since it occurs on the right side, you add 2 to 5, so it becomes 7. But when 1 comes on the left side, you subtract 1 from this 5, therefore it becomes 4. But here also it was 1, here also it was 1. The position really did not affect the value of that number. Same here. Here you have 10, 5 and 1. So since these are smaller to the bigger number, right side of the digits are smaller to this number. So you have 10 plus 5 plus 1 is 16. Now you have a big number and you have a smaller number on the left side. So you subtract 1. So it becomes 9. So symbols represent the value irrespective of the position. The problem with this Roman number system is it's extremely cumbersome or difficult to perform arithmetic operations. So we have the Arabic number system or the Indian number system or the decimal number system, which is very widely used. Now, in a positional number system, as I gave you an example, I showed you this example of 2, 3, 6 and 6, 2, 3. The position of the digits really affect the value. The 2 here is not the same 2 here. The 6 here is not the same here because its position requires ones to be multiplied with 100, ones to be multiplied with the units number. So what is the base or radix of a number? The base or radix of a number is how many unique digits are there in that particular number system. For example, in decimal number system, there are unique digits from 0 to 9. So there are 10 unique digits. Thereby, it is called as the decimal or base 10 number system. Binary has only 2 unique digits, 0 and 1. So it is called as the base 2 or binary number system. Now just take a look here. The decimal number system is the most common number system which we tend to use. It's got unique numbers from 0 all the way to 9. Therefore, the base or the radix is 10. Now let's try to understand how this decimal number 542.760 in base 10, how its individual parts create the final value of 542.760 based upon their position. So if you look here, what I do is, this 0 represents 10 raised to minus, 6 represents 10 raised to minus 1. Okay, and if you see here, 0 I've ignored, sorry, 0 should be 10 raised to minus 3. So 6 is 10 raised to minus 2, 7 is 10 raised to minus 1, 2 is in the units position, 4 is in the tens position, 5 is in the hundreds position. That's why you have its weight as 10 square. So when you take a different number, okay, you give it something called as the weight. The weight of 5 is hundredth, the weight of 4 is 10, the weight of 2 is units, the weight of 7, since it comes after the decimal place, is 1 upon 10, 6 is 1 upon 100, that is its weight. Now if you look at the individual digits, they are 5, 4, 2, 7 and 6. So if I have to get this number, what I can do is I can multiply 2 into 10 raised to 0. What is 10 raised to 0? 10 raised to 0 is 1. 2 into 1 is 1. 4 into 10 raised to 1 is 10. So this is 40. This is 242. 10 into 10 is 100. So this is 5 into 100 is 500. 500 plus 40 plus 2. So this side becomes 542. Now what about 1 upon 10 is 0.1. 7 into 0.1 is going to be 0.7. This is 1 upon 0.01. So 6 into 0.01 is equal to 0.06. So we need to add all of this. So here it is clearly shown. 5 into 10 square, 4 into 10 raised to 1, 2 into 10 raised to 0, 7 into 10 raised to minus 1, 6 into 10 raised to minus 2. And here if you see, it becomes 500 plus 40 plus 2 plus 0.7 plus 0.06 is equal to 542.760 to the base 10. So this is how a decimal number is represented based on the weights. So different positions have got different weights, and based on the weights you are able to get the value of the final number. So weights is, this is 10 raised to minus 3, 10 raised to minus 2, 10 raised to minus 1, 10 raised to 0, 10 raised to 1, 10 raised to 2. If there was one more number, it would be 10 raised to 3. So if you take the digit and multiply it by the weight, you will get the value of that particular position. So the value of 5 is 5 into 10 into 10, which is 500. The value of 4 is 4 into 10, which is 40. The value of 2 is 2 into 10 raised to 0 is 1. So 2 into 1 is 2. This is 10 raised to minus 1 is 0.1. 7 into 0.1 is 0.7. 10 raised to minus 2 is 0.01. So 6 into 0.01 is 0.06. So when you add the sum of all of these, you're going to get the final number. So I hope you have had a basic idea of what are weights, what is positional number system and non-positional number system. An example of a positional number system is your decimal number system. Non-positional is your Roman number system. The base or the radix represents the number of unique digits in that particular number system.